Hi guys, welcome to 8.1, Exploring Exponential Models. This is going to be separated into two separate lessons. We're going to do the first objective right now to model exponential growth, and we'll do model exponential decay on the next one. Examples 1 and 2 are fairly easy. It's stuff that you have seen before in the past, hopefully, and although it's something you haven't done in a while, it should be something you remember, kind of like riding that bike. Now, example 3 is the more tedious, difficult one, and it's okay if you look at it from the perspective of you're solving a puzzle. You have to do one thing before you do another, sort of like the composite functions that we had done in chapter 7. So, all right, let's go ahead and get started. Okay, so in exponential growth, an exponential function, the general form is right up here. The y equals ab to the x power. Okay, so that's your general everyday form. The a represents what you're starting with, what you're beginning with, what your beginning value is. Excuse me. B represents your growth factor. In order for that to be a growth factor and not a decay factor, it has to be greater than 1. If you're given your rate in the form of a percentage, you obviously have to convert that to a decimal, add that to 1, and that's your growth factor. All right, so looking at example 1, graphing exponential growth. We are going to rely on our good old friend, wow, the t-chart. Now, you are going to want to pick values that are easy for you. It doesn't matter what they are. You can pick really obnoxiously large or really ridiculously small numbers, or you can pick just some safe numbers, but I would be careful with picking too big of numbers because they won't fit on your graph unless you scale the graph. And I would highly recommend if you scale the graph that you do the tick marks the same scale. It just gets really awkward when you do more than like the x-axis as 1s and the y-axis as 5s, as you've seen in class. It just doesn't work out so well. All right, so I am going to pick my favorite 5, -2, -1, 0, 1, 2. I always use these just because they're the easiest. That's all it boils down to. All right, so we have 3 to the -2. Well, this negative here tells me I need to flip my base. So this gives me 1 over 3 squared, which is 1 over 9. The second one, we have 3 to the -1. Again, this negative tells me I need to flip my base. So that's going to give me 1 over 3 to the first power, which is just 1/3. Then I have 3 to the 0. Anything to a 0 power is 1. 3 to the first is just 3. And then we have 3 squared, which is 9. Okay, so now we need to go over to our grid, and we need to plot these points. All right, so we go to -2 on the x-axis. There's the origin, -1, -2, and 1/9. Well, shoot, that's really small, so let's put that close to the x-axis. -1 and 1/3, well, that's still relatively small too. 0, 1, 1, 3, and 2, 9. So we've got 3, 4, 5, 6, 7, 8, 9. Oops, there we go. All right, so now we want to draw our line, it's not a line, our curve to model this growth, and it's going to be approaching from negative infinity. This is negative infinity. Oh. Oh. Negative infinity over here. This would be approaching positive infinity over there. So it's going to be coming from negative infinity, and it's going to really, really close to that x-axis. And then as soon as it hits up here, it just takes off That's a horrible graph. um, but essentially, that's what all exponential functions look like. They have some sort of curve that real close to one of the axes, and then it just takes off. Okay. All right, so let's go ahead and go to example 2 because I don't want to take too much time. All right, here we have one where we're going to have to do that growth factor. Okay, we're going to have to create our own equation. And this is what I was referencing, where you have to convert that R to a decimal. It cannot be in the form of a percent. It has to be in the form of a decimal. All right, so the population of the United States in 1994 was almost 260 million, with an average annual rate of increase of about 7.7%. Find the growth factor for that year. Okay, so we know the rate of increase is 0.7%. Now we're looking for the growth factor. So the growth factor we know has to be greater than 1. All right, since we're given that the rate is 0.7%, we know in order to get the decimal, we need to move that 2 places to the left. So that gives us 0.007. Therefore, your growth factor is equal to 1 plus 0.007, which is 1.007, right? Because this, the B up above, is 1 plus R. Okay. All right, so we've got 1.007 as the growth factor. Now, for part B, it says suppose the rate of growth had continued to be 0.7%. Write a function to model this population growth. So we are going to come down here, and A, remember, is our starting amount. B is the growth factor. And then X would represent the number of times it has increased or grown. Usually it's once a year, but sometimes you'll have them every 3 years or every 5 years, and you have to figure out how many times has it grown over the course of that period of time they give you. Okay, so going back up to the data, it says the population in 1994 was almost 260 million. So that's our starting amount. So A, oh, I thought I changed colors. Sorry. A is 260. B we found up here, which is 1.007. And then the X we don't know. So to write a function to model this population growth, we would have Y equals 260. I'm going to put this, the growth factor in parentheses. It just makes it easier than putting a dot there because sometimes that dot looks like a decimal. So we have 260 times 1.007 raised to the x power. And there you go. Looking above at the example above, because I know there was another part to this up there, maybe not. I thought it said use that function to model the population in like 1997. If that's the case, you would say 1997 from 1994, or 1994 from 1997, that's 3 years. So you would put a 3 in for your x, put that into the calculator, and you have your answer.